formula. If you have a lamina, same thing, has a variable density. These are all in your book, by the way, and they're all in your notes too. Then one of the most interesting things to find, in terms of a lamina, is its center of mass. Especially if the lamina does not have the same density throughout. Like if you have a flat sheet of paper like this, a rectangle, and it's homogeneous, which means the density is always the same, the center of mass is pretty obvious, right? It's just the center of this. But if this is no longer homogeneous, then the center of mass could be just about anywhere, right? And there are even some objects where the center of mass isn't even on the object. A boomerang is an example of an object that has a center of mass outside of its space. And another one you could take is like just a disk like this. Its center of mass is there, right? Even if it's homogeneous. So finding the center of mass is computed. The center of mass is a point. It has an x and a y coordinate. We call it x bar, y bar. And look at what you do to compute the x and y coordinates. To compute the x coordinate, you have to take the moment and divide it by its mass. To find the x coordinate of the center of mass, you take the moment about the y-axis and you divide it by the mass. Remember, this was the moment, right? I know everyone's tired, but don't help them out. All right, thank you. All right, that was the moment formula, and then we just 1 over mass means divide by mass. But what was mass? Yeah, but wasn't the mass a different double integral? So in order to find the x-coordinate of a lamina, center of mass, you have to do 2 double integrals. One double integral gives you the moment, and you divide it by another double integral, which gives you its mass. And then to find the y-coordinate, it's the other moment divided by the mass. So if you're given a problem where you're asked to find the center of mass of a non-homogeneous lamina, you have to compute 3 double integrals. You have to find the mass, because you need it for both of these, and you need to find both the moments. Here's an example where you're asked to find the center of mass of a region bounded by some things, and then I give you the density function here. What I wanted to do with this was to just show you, like, this is the lamina. It has a variable density. So can you see that the darker shades represent where it's more dense, and the lighter shades where it's less dense? How dense it is depends on the x value. For this particular density function, the x value dictates how dense you are. So the bigger x is, right, the bigger your density is. And I actually did this 3-dimensionally so you could actually pop it out of here. And whoa. You could kind of get an idea of how much more dense that object is out here towards this edge with the height. Now, it's not 3-dimensional, but it just gives you some idea of how much of this object's density is over here. So its center of mass should be way over here somewhere, shouldn't it? It's not going to be right in the middle. It should definitely not be, right? Center of mass should not be like right there. It should be this way. So to do it, I only have 2 minutes, 3 minutes, 4 minutes. This was y equals negative 2x plus 6, and this is y equals x. So that's, if you were to draw this region out, that's what you would get. And so you would need your limits of integration. This would be a good type 1 region. So you should go double integral. Let's do the mass first. Mass would be double integral where to where? Well, you have to figure out what's your bound on x. 0 to wherever they hit each other. So you set those two equal to each other, okay? It's 2, all right? I think it's 2. 2 2 in here, 2, yeah. So if you plug in 2, you should get. And then what's the lower and upper bounds here? Y equals x on the bottom and negative 2x plus 6. Now for mass, what am I integrating? Just the density function, x squared. dy dx. You figure out what this is, and you get a number, right? That's your mass. Put it to the side. You'll need it later. Then you come in here, and you do the moment, right? So if I want x bar, it's the moment about y over mass, which is 1 over mass times the double integral of what? What changes? These are opposite. I'll go back to the moments. So look, moment, a moment about the y-axis, you use x in here. A moment about the x-axis, you use y. That was it. So it would be x times that, so x cubed. dy dx. What about the limits? Exactly the same. So you're doing almost the same integration, right? Except you're doing x cubed instead of x squared. And then when you do y bar, it's moment about the x-axis over mass, which is 1 over mass, double integral. Those limits still stay the same. And now this time, instead of x cubed, it's yx squared, or x squared y, dy dx. Now that integration is going to be a little different, right? Because now you have a y in there.
Does the dy dx always stay the same?
Yes, because it was a type 1. Because we chose to do it as a type 1 region, right? We decided to go this way with it. You could do type 2, but it would suck because you'd have to break it into two pieces. Yes? You could use, if this region was, if that region looked like you should do it polar, then yeah. What about on the take-home? Aren't you asked for a mass? Yeah, but it's not, yeah, I don't think that's, whoa, do I not give you, whoa, there's no, I don't give you any restrictions. What the hell? We need to fix that. I didn't give you any restrictions on that, did I? Okay, hang tight, or else you won't be able to do number 4.
On the X bar and the Y bar?
Yes?
On the notes, it's multiplied by Y for X bar.
Mm-hmm.
Inside the integer, can you get X?
What did I do? Hold on a second. 0, 0, 1. Okay. For X bar, where did I reverse it? You sure?
On my notes, my notes like different than yours.
What does yours say?
On the X bar, it's multiplied by Y. Well, it was like an actual shape.
Who has the book? I do. Okay, so look, on number 4, let's fix that first. On number 4, the region is the region, this is y equals e to the x. This is 1, this is 0. So it's the x-axis. Okay. I don't know where I want to do this. The moment equations are correct. Does that match what you have on your notes? The moment equations, there they are. Yes? So the moment of the lamina about the x-axis, it's y times the density function. Moment about the y-axis, x times the density function. And then x bar is the moment about y divided by m, which is 1 over m, and then this right here is the moment about y. So x times the density. Is that not what I have there?
Yeah, you're right.
So it's okay there? I'm just making sure it's not a typo.
No, yeah, it's okay.
Okay. And then the y bar is the moment about x over mass, which makes that a y. Okay, did I resolve number 4 as far as what the region is? Now, on number 4, doesn't it ask you to compute the moments of inertia also? So you should be able to do part A. You should be able to do part B. Part C is moments of inertia. And just look in the notes, okay? There's two more formulas. Moments of inertia, there's these 3 formulas. Moment of inertia about the x-axis is almost like the moment about the x-axis. Instead of multiplying by y, you do y squared. The moment about the y-axis, instead of multiplying by x, you do x squared. So again, it's very similar. Now, anyone know what the moment of inertia is? It's if I take, I'm sorry, I'm keeping you late. If I take this lamina, okay, flat sheet, it has a mass to it. And let's imagine that I want to take it and rotate it around the x-axis, 3-dimensionally, right? It has mass, so I have to push it, right? And anything that has mass resists motion, doesn't it? So if I go to push this, it's going to have a resistance. That's your moment of inertia. If I move this further away from the axis, it changes its moment of inertia. Its resistance to motion. So the last question there is to determine with calculus if it is easier to rotate the lamina about the x-axis or y-axis. So that means you need to calculate these 2 moments of inertia and compare your 2 answers to answer that question. I'm going to leave that to you to figure out. I want you to think about it, and if you can't figure it out, I want you to look it up. Think about a door. Think about a door. If you go to open that door, if you pull it by the handle, it's going to be easier than pulling it by a handle in the middle of the door, right? So maybe that helps. I don't know. Okay? I guess have a good day. Kill this real quick. Oh, shit.